So folks, here we're presented with solving this matrix differential equation. Remember that we got this matrix differential equation by taking the original system of equations and representing it as a matrix differential equation. And then also in the previous example, you should have found that there were two eigenvalues, eigenvalue of 3, eigenvalue of 2, and you should have found associated eigenvectors for each one of them. Remember that eigenvectors aren't necessarily unique to the eigenvalue. In this case, since the eigenspace is of dimension 1, as long as your eigenvector is simply a multiple of my eigenvector, then we're in agreement. We found an eigenvector associated with the eigenvalue 3, and likewise we've got an eigenvector associated with the eigenvalue of 2. So now that we've got that, we can now talk about how to represent the solutions to these matrix differential equations. The work that we're going to do in class is going to justify what we do here, but sort of similar to when I asked you to solve the differential equation y prime is equal to 3y or something like that, we remember that the exponential function was a solution to this first order linear differential equation, linear homogeneous differential equation. We'll have the same thing, something very similar, when we go to solve our systems of equations. What we'll find, and this is the work we're going to develop, and this is why I'm saying we're going to naively solve this, what we'll find is that the solution of this, x, is going to be c1 e to the lambda 1, so 3t, times our eigenvector, and our eigenvector that we picked for when lambda was 3 was negative 1, 1, plus c2 e to the second eigenvalue, e to the 2t, and its associated eigenvector that we came up with was 1, 2. So 1, 2. There are other ways we could represent this solution, but notice how we can recover the two solutions from this statement. This, recall that we said that x bar was just the matrix of the column vector of the functions x1 and x2. So we could go ahead and say that x1 is equal to c1 e to the 3t times negative 1 plus c2 e to the 2t times 1. Or if we rewrote that, we'd get x1 of t is equal to minus c1 e to the 3t plus c2 e to the 2t. And our x2, we read off, gives us c1 e to the 3t times 1 plus c2 e to the 2t times 2, or that is our x2 of t is equal to c1 e to the 3t plus 2c2 e to the 2t. And there we've got the two solutions that solve both of these original linear differential equations simultaneously, and you could verify that. So what I want to point out then is that in general, if you have for an n by n system n distinct eigenvalues, then we'll always be able to represent our solutions this way. So if for a 2 by 2 system we have two distinct eigenvalues, let me say two distinct real eigenvalues, lambda 1 and lambda 2, with eigenvectors v1 and v2, what we'll do in class is we'll show that this gives us a general solution. X of t is c1 e to the lambda 1 v1 plus c2 e to the lambda 2 v2 is a general solution. So in class we'll justify that what I just did here is in fact the general solution. Let me box that. That is the general solution to the system of differential equations. And likewise, that would be the case for any situation where we have two distinct eigenvalues and their associated eigenvectors. What will be more difficult in some of the work we'll be doing is what do we do if we get complex eigenvalues and potentially then complex eigenvectors? Or what do we do in the case, and this will be the hardest case, when we have repeated eigenvalues? So notice that when I went through to find the roots to the characteristic equation, we got that lambda equals 3 and lambda equals 2 were roots to the characteristic equation, but they were each of multiplicity 1. The hard part will be what do we do when the multiplicity is something greater than 1? And that'll be something that we see as we go forward. But for right now, my goal was just to give you a quick overview for what we're doing when we solve these systems of linear ODEs. And in this case, we took the system of ODEs, we represented it here as a matrix equation. Then we went ahead and found the eigenvalues and eigenvectors of the coefficient matrix A. And then we were able to represent our general solution as C1e to the first eigenvalue times its associated eigenvector plus C2e to the second eigenvalue times its associated eigenvector. And that gives us our general solution. It will be harder, as I said, when we have repeated eigenvalues or when the eigenvalues are complex. But for right now, this gives us a nice overview. In the next video, we'll look at quickly graphing this solution.